and we haven't given neither one of the initial or final pressures. So the question is, can we actually use this equation? Well, because we have two unknowns here, we need something else. We could, for example, write down the ideal gas law. The ideal gas law always applies, and it kind of looks like that this one here is a new ideal gas law, and it's not. It's actually the same as this one over here. And of course, yeah, you can argue definitely there is an exponent here that doesn't exist over here. But what that exponent does here is it gets rid of the temperature, which during an adiabatic process changes, and in getting rid of it, it introduces that adiabatic index. So this one here is kind of an abbreviation for the ideal gas law having kicked out the temperature. It only says pressure, volume, and keep in mind the temperature does change, and the exponent gamma is substitute instead for that. Now, what we can do is we can take this formula and plug it in here, and then derive something that has something in temperature and volume, with again the gamma in there as an exponent, and then we can do the same thing for pressure and temperature. So all these three variables, P, V, and T, can be thrown around, and the adiabatic law can be made look can look a little bit different. By the way, in the book, all they say about the derivation of that equation is that it's done by integral calculus, and this is, I got this here from Wikipedia, and if you were to follow this one here on the adiabatic process on Wikipedia, indeed that's what they do. They introduce another parameter called alpha, and then at the very end they substitute the gamma in for this alpha here, and there it is, PV to the gamma. And then, as I said, for the others they would do something really similar, like, let's see, boy, where'd it go? I think this is the one. Yeah, here's the one for temperature and pressure, and then somewhere in between is the one for temperature and volume. At this point, my solution manual says, take the ideal gas law, plug it in here on both sides, get rid of the pressure that we don't know, and then what we are able to introduce is the V here and the T, and we come up with an equation in volume and temperature, and therefore can solve then for the only unknown that's left, the volume here. But there's a second way of doing it, because when we look at the ideal gas law, again, this is applicable at all times anyway, then notice that for the initial part we have the initial volume, we have the initial temperature, we know it's 1 mole, and so all we need to do is solve for pressure. There we go. And come up with nRT initial, which we know, divided by the initial volume. And so that comes out to, let's see, 1 mole times 8.31 times 393 kelvins divided by the initial volume of 0.1 cubic meters. So it's all in standard units. And I come up with a pressure of, let's see, 3 significant figures, 32,700 pascals. Okay, and that means now I know what the left-hand side is going to be. The left-hand side, therefore, is going to come out to 32,700 pascals times, and I'm going to use here on my calculator, it says 32,658.3, so I'm just going to use that one, times the initial volume of 0.1 cubic meters, and that needs to be to the 5/3 power. That's the adiabatic index, and I come up with, on the left hand side, with 704 rounded, 703.60, 704 rounded, equals PF times VF to the gamma. And then I notice I actually do have to plug that in because I still have two unknowns here, and here I also have two unknowns with the final temperature given. So I'm going to plug this one in here anyway. So I'm going to have 704 equals, and getting rid of the pressure that I don't need, I'm going to say nR TF divided by VF times VF to the gamma. And actually in hindsight it does look quite convoluted at the end. 704. There was nothing better to do. This is of course a 4 as usual. nR TF, which we know, times VF to the gamma minus 1, one of the laws of the exponents. And then to solve for VF, it would be 704 divided by nR TF parentheses, and then in order to get rid of the gamma minus 1, I need to take the root on the other side, and that can be written as such: 1 over gamma minus 1, again with some law of the exponents, and I come up here with something, and because everything is in standard units, this will also come out to cubic meters. And then I might as well do it. So I'm going to do this one up here. I'm not going to write it down, by the way. So I'm going to do this one up here, which says negative 825 joules divided by parentheses 3 over 2 times 1 mole times 8.31 parentheses, and then add to that the original 393 kelvins, and I come up with a rounded 327 kelvins right here. And then I take the 327 kelvins and plug it in right here. So this is going to be 704. Remember, this is always smeared. Whenever the software gets a chance, it smears out the 4. That's a 4. This is a 4. There we go. So parentheses 704 divided by 1 mole, or again another parentheses, 1 mole times 8.31 times the 327 kelvins that I just calculated, close the parentheses again, and then to the 1 over 5/3 minus 1. And I have to close again several parentheses, and I come up with a rounded 0.132 cubic meters, and that's what I said earlier, that so 0.132 cubic meters, that the volume of course has to become larger as it expands.